So we did cylindrical coordinates. Now we're going to talk about spherical coordinates. So the way that spherical coordinates work is you essentially, like, you know, if you think about, so if I were to just draw a new axis real quick, the way it basically works is you take in a certain kind of distance from the origin, rho, right? So you need a rho and you need an angle. You need an angle theta from the x. Let me draw it in real quick. So let's say you had a point x, y, z right here, right? Well, in cylindrical coordinates, what it would look like is it's a distance rho away from the origin. It's going to be an angle, so this is kind of weird. It's going to be like an angle phi. It's going to be an angle phi from the z-axis, and if you were to drop this down to the xy plane, it would end up being, if I were to draw this, an angle theta from the x-axis. So angle phi from the z-axis and an angle theta from the x-axis. So that is how you define spherical coordinates. So if you can imagine, it kind of reminisces you of a sphere, right? If you set rho to be constant, right? So for the equation rho equals like 4, that would be a sphere, right? With a radius 4, because this represents all points where the distance from the origin is equal to 4. If you imagine setting theta equal to, like, let's say theta is equal to pi over 4, so I don't have to draw a new one, that would actually look like a plane, because that would consist of all points. It would actually be a half plane. It would be a plane like this, because this represents all points where that sort of angle is, the angle from the x-axis is always equal to pi over 4. And if you were to define phi is pi over 4, right, this would actually end up being a half cone. It would not be a full cone, right? A full cone, at least in a multivariable, it's kind of like, it would extend the other way. But for something like this, you could see for all points, the angle phi is a constant pi over 4. So that would be a cone, right? That's just to give you an idea of kind of what kind of shapes, polar coordinates make. And you can integrate these, right? So when we're doing triple integrals, we can actually use spherical coordinates. Did I say polar? I meant to say polar. Spherical coordinates, right? That's what we can use. So if you imagine if you had like a sphere, like a solid sphere, and you're in our usual rectangular way, we would do our dx, dy, dz, and kind of slice them up in a really small little delta v, right? And when you integrate, when you do your triple integral, it's the limit as that becomes dv, right? So you're taking all the dv elements, the chain, like the small little bits of volume. If you were to do the same thing here, well, what it would look like is you would have this sort of spherical wedge, right? This would be our change in v, right? So we're saying this, right, is change in v. And what is the volume? Well, as you keep, making these wedges really, really, really small, right? That's the goal of an integral, is we want to get as small little kind of sections to integrate as possible. Well, it's going to essentially approximate a box, right? And it's going to be a box with certain dimensions, right? So if you think about length times width times height, that's going to equal the volume. So for one of the side length, it just ends up being the little change in rho, right? As you're doing your triple integral, you're going to be going along all the little delta rows, or the d rows, and the side length will end up equaling delta rho. So that's kind of like the one length. Now, what would this kind of equal? Well, this actually ends up equaling an arc, right? This is going to be an arc, and I have to kind of think this through. This, I believe, if I'm not mistaken, I drew this terribly. Let me look at my book. I drew this terribly. I'm even getting caught up in my own sort of thing. Oh, okay. Now it makes more sense. I had to look at the picture and I had to see. We have this delta rho element. Now, we're also going to be integrating and changing the phi variable, right? If we think about a sphere and we're going to start integrating this way, there's going to be this right here. This sort of angle represents delta phi. Or I should really say change in, or delta phi. Yeah, there we go. So by arc length, right, this will equal rho. So multiply by rho times delta phi. And then this is going to be kind of hard to see. If you think about spherical coordinates, let me actually do this now, talk about some of the bridge equations. Let's say I wanted to bridge, so if this is a point x, y, z, right? If I wanted to bridge over, well, first of all, hopefully you can notice that rho squared, right? This distance squared just equals x squared plus y squared plus z squared. So that's our kind of first bridge equation, equals, so rho squared, and bridge equation meaning bridging between spherical and rectangular coordinates, x squared plus y squared plus z squared. Now, if we wanted to first of all find z, that's actually pretty simple, right? If you think about the height, this actually forms, if I make this dotted, this forms a right angle, right? With the xy plane. So if this angle right here is phi, that means this angle right here is phi by geometry. Like if you were to imagine like the same sort of parallel kind of line going there, by parallel angles it would end up being, or by alternate interior angles I believe, they would end up being congruent. So rho times cosine theta is equal to z. And then if you think about, well, what is this side length, right? This side length is rho cosine phi. So the other, or phi, I don't even know. This one is rho sine phi. So if you now imagine this angle theta, right? I kind of drew this wrong. If you imagine this angle theta, right? This side length is rho, it's kind of crazy. It's rho sine phi, right? That represents this diagonal distance times cosine theta, right? Because now I take the cosine, because this is another right triangle that's formed. This right here is rho sine theta, or sine phi sine theta, yeah. So if I bridge this over, hopefully you can kind of see I drew that wrong, but if I bridge this over, I get x is really rho sine phi cosine theta. Y is rho sine phi sine theta. And then z is really rho cosine theta. Okay? And hopefully the x and y kind of makes sense, because if you think about it, when we're doing spherical coordinates, this rho sine phi right here, right, that I'm about to just thicken up, this just represents r, right? This is kind of like our r from spherical coordinates. So this is like r cosine theta, r sine theta. So it's kind of consistent. It's just now this represents rho sine phi. So the point of showing you that was this side length right here, right? If you think about kind of our picture, this is this angle theta. So, oh my God, this picture's terrible too. Let me look at my own picture. Does it kind of look? Okay, yeah, this is what I wanted to show. So this side length right here extends all the way down here. So this side length right here represents this length right here. And this, this angle right here is delta theta, because it's like small little change in theta. So this would essentially equal rho sine phi, right, by just kind of what we derived here. So this side length is going to be, so this side length right here by arc length is rho sine phi times delta theta. Now, when you take the limit, right, we get that dv, right, when we make these really, really small dimensions, we get dv is equal to, so I have two rho's, so rho squared. I have this sine phi term, and then I'm going to multiply by d rho, d phi, d theta. So this is kind of our differential term that we're going to use in our integral. So dv equals rho squared sine phi, d rho, d theta, d phi. I'll just do it in that order. I think those are the pretty crucial bridge equations. And once we know these bridge equations of how we can bridge over from rectangular to spherical, this we can use as an integration technique. So let's actually just start off with example 1. So I just dropped my eraser. That's fantastic. So let's do example 1. All right, so you may have noticed a cut. The first example, I realized I grabbed it from my cylindrical coordinate notes, which I swear, like this one I'm confident is from the spherical coordinate notes, example 2. But example 1 was a cylindrical problem, which is why when doing it, I realized, wow, this is, it feels very complicated, and I just pulled them from the wrong notes. Let's do example 1 now. So with example 1, we're going to, let's first of all just draw the region that we're integrating under, right? It's the triple integral of 9 minus x squared minus y squared dv, where e is the solid underneath x squared plus y squared plus z squared is less than or equal to 9, and z is greater than 0. So it's basically a hemisphere. So it's going to be a hemisphere, kind of like this. You can draw it like that, sure, like a little dome. In polar coordinates, or in spherical coordinates, right, this is where rho is equal to 3, right? These are all points where the radius or rho is equal to 3. So when we're doing our triple integral, let's first change this. One thing you might notice is if we think about our triple integral that we got going on, right? The function that we're integrating, oh my god, I drew a 9 too early when I'm supposed to be taking a triple integral. So if we have this triple integral, we are going to do 9 minus, and I can factor out a negative. I get x squared plus y squared when I factor out the negative. X squared plus y squared, that's just, if we think about our bridge equations, that's actually just rho squared sine phi squared, right? Because it's just, if this was x and this was y, this would end up being the hypotenuse as we kind of derived earlier. So I can even just change this out, start converting this to spherical. This is just rho squared sine squared phi, and then we need our differential dv. So this would be rho squared times sine squared phi, and then we can get our d rho, d phi, d theta. What are our bounds? So if we think about this, we're going to be integrating from rho is equal to 3 to rho equals 0, right? We're integrating everything that's within the sphere. So we're going from 3 to 0. For our, now let's think about phi, right? The hemisphere only goes as far as phi is equal to pi over 2, and then it goes to phi equals 0. So we're going from pi over 2 to 0. And then for theta, right, the x-axis angle, we're doing a full revolution. So that would be 2 pi to 0. All right, so now what we can do, to solve this, we're doing d rho first. So if we distribute, let's actually just distribute it here. It should be a sign. So we get 9. So when we distribute things over, we get 9 rho squared sine phi minus rho. So we had rho squared times rho squared, so it would be rho to the 4th sine to the cubed phi. And then we have the d rho, d phi, d theta. So let's just go ahead and let's do the rows first, right? So when we take the antiderivative, it would be 1/3 rho cubed, and then 1/5 rho to the 5th. So let's go ahead and get that going. Everything else, right, we regard as constants. Hopefully that's kind of a concept you're familiar with by this point in multivariable, the idea of treating other variables as constants when we're doing something with respect to one variable. We're going to do, so it's going to be 9 sine phi times 1/3. You know, it's going to be 3 cubed, right? We would do 3 cubed minus 0 cubed, but 0 cubed is just 0. So 1/3 times 3 cubed is 27. Minus, so we're going to have sine cubed phi. And then here we're going to have 1/5 times 3 to the 5th. And this actually ends up being 243. And I'm going to have to make sure I'm doing everything right because sometimes I make mistakes. All right, let's do d phi next. So here's the deal. First things first, you can factor out a sine phi. Wait, am I doing everything right? No, you can't factor. Oh, you wait. See, this is the thing where I make mistakes. I feel I've definitely done something wrong already. Oh no. I haven't. Okay, we're just gonna leave it like this. Okay, we're just gonna leave it like this. I don't. Oh, okay. I can factor out a sine phi. It's just it would end up having integration by parts. Oh my god, I don't know why I'm making all these mistakes on camera. It's a little bit embarrassing. I thought that through when I was doing the problem, but I don't know. Maybe I'm just not good. I just can't think on the spot. Well, we're gonna kind of do these separate. You know what? Let's just do it like this. So we're gonna have to deal with this. So first of all, 1/3, or a third times 27 is 9. So that would 9 times 9 is 81. So I would have this would really be 81 sine phi, and this right here, right? This would end up being just plain and simple 243 over 5 sine phi. So let's go ahead and take these integrals separately. So for this case, we get 0 to 2 pi times 81. Now, here I have 81 times the antiderivative, right? Because I'm taking this a double integral, or taking this inner integral first. Sine phi, it's going to be negative cosine. So it's going to be negative cosine pi over 2 minus negative cosine 0. This becomes 0, right? Cosine of pi over 2 is 0. And this is negative 1, but we're doing negative 1. So we'll just say negative 1. So this whole thing becomes 1. So now I have 81, d theta minus integral 2 pi to 0. Now this is where it gets a little bit crazy because we're going to need to evaluate sine cubed. So if you think about, okay, let's have sine cubed phi d theta here, and then I'll evaluate kind of on the side d phi. We're going to go from pi over 2 to 0. So sine cubed, this is the same as sine times sine squared. And sine squared, that's just the same as 1 minus cosine squared. So 1 minus cosine squared phi d phi. All right, so now we can actually do u cell. We can say u is equal to cosine phi. Du is going to equal negative sine phi d phi. So I can pull, I'll have to put a negative out here. But u of cosine phi, right? Or u of pi over 2, what am I saying? Is equal to 0. U of 0 is equal to 1, right? Because I'm just doing cosine pi over 2 and cosine 0. So I would have a negative out here because I need a negative here, but this would actually, the negative would flip the bounds. So I would get 1 to 0, 1 minus u squared du. So this would be u minus 1/3 u cubed from 1 to 0. So I actually get 2/3. So, I kind of just solved it. I just solved it here, I guess. So I essentially get 2/3. So I get 243 over 5 times 2/3 d theta. And then there's no theta in either of these, so this is just the same as multiplying by 2 pi. So I get 162 pi minus, I get 243 times 2 is what? 486. And then 486 times 2 is 872. So I get 872 pi over 15, but that's off from the answer key. Or did I make a mistake? 486 pi over 5? Is that the right answer? Wait, let me check. Let me use I have a calculator right here. 162 minus 872 divided by 15. And then what was the answer here? This actually might be right. I might have just did it differently from them, but 486 divided by 5. Nope, I'm off by a little bit, and I don't know where. Where could I have been off? Did I do this? Did I do all my 486 times 2? Oh, it's 972, okay. Oh, yeah, I even drew a 1 there. I am spending a lot of time on this. Yeah, okay, I got it. I guess right. Oh my god, that I need to not spend so much time. But you know what? It's fine. So let's do the next example. So we want to find the volume of a solid underneath z equals root x squared plus y squared, and within this sphere, x squared plus y squared plus z squared equals 2. So if we want to just draw this region, hopefully you notice that this is a half cone, right? The z equals root x squared plus y squared, because usually a cone is z squared equals x squared plus y squared. But this is just taking the square root on both sides and leaving us with only positive values of z. So therefore it's a half cone. So I have this half cone, and then I have this sphere that is with radius 2. And I want to find, I want to find the area underneath the cone, but still within the sphere. Now, so if I'm doing any kind of volume triple integral, it's just triple integral dv, right? We're integrating 1. So this is the volume is going to equal, so triple integral, and let's just get our differential in there, right? Rho squared sine phi d phi, or d rho squared d theta d phi. So if we think about our bounds, I'm so sorry. When we think about our bounds, we're going to be integrating, right? We're going to be integrating from essentially 2 to 0, right? We're integrating. It's kind of hard to explain because we are integrating the full thing, but we're stopping at this cone. And first of all, I guess I should just point this first. What is this? Or actually, we'll get there. But yeah, we're gonna stop at this cone, but we're still integrating, I guess, from 2 to 0, right? I know it's a little kind of confusing because it's usually like, well, we're stopping at this surface, so, but we're going from 2 to 0 because really the condition that's constricting this is the phi, right? This is a constant phi. What you can actually do is you can kind of say, okay, well, z I know is equal to rho cosine theta, right? Rho cosine, or phi. I wrote theta here. That's awesome. The entire video. And then I have square root. Now I'm gonna be doing square root rho squared. This is just rho squared sine squared phi. So this, if I get rid of the square root, it's rho sine phi, right? And I'm only worried about positive values, so I'm not gonna worry about the plus or minus, I'm not really gonna worry about the plus or minus. And then I essentially get, the rows drop, and I get the solution to this is phi equals pi over 4, right? Because if I divide everything by cosine, I get 1 is equal to tan, and the solution to that is pi over 4. So I'm going from pi over 2 and I'm stopping at pi over 4. That's kind of the constraint. So pi over 2 to pi over 4, and we're doing a full revolution, so it's going to be 2 pi to 0. All right, let's solve this. So this is the antiderivative. When I'm doing d rho first, it's going to be 1/3 rho cubed, so pi over 2, pi over 4, 2 pi to 0. So 1/3 and then 2 cubed minus 1/3 0 cubed, 0. So this becomes 8/3. So I'm doing 8/3 sine phi d theta d phi. All right, awesome. So we're gonna have volume is gonna equal pi over 2 to pi over 4. There's no theta in this equation, so I can just put, it's just gonna be multiplying by 2 pi. So I get 16 pi over 3 times sine phi d phi. Now, the antiderivative of this is negative cosine. So I get 16 pi over 3. So negative cosine. So negative cosine pi over 2 minus negative cosine pi over 4. So this becomes positive, so I'm really adding, and cosine pi over 2 is 0, and this is root 2 over 2. So my final answer is volume is going to equal 8 root 2 pi over 3. So yeah, there you go. That's that's integral integrals and spherical coordinates. Once you understand the bridge equations, this is just another strategy to help you tackle integrals. Because you could technically do these by hand, you probably can, but these make it, spherical coordinates makes it a whole lot easier. So yeah, thanks.